people, welcome. Wow, this is loud. Okay, welcome to my presentation about using AI to save time and sanity. No worries. So in the next 45 minutes or so, I'm going to introduce you to the AI lab that I'm coordinating. So I'm a professor at Utrecht University. I'm coordinating one of the official AI labs. So if you ever plan to work at a university and are interested in a job at one of the AI labs, let us know. I'm coordinating the AI lab on AI-aided knowledge discovery. And in this AI lab, we coordinate a lot of projects about using AI, or actually AI is a very fancy word, right? So it's just machine learning. We coordinate a lot of machine learning projects to answer societal challenges. We run a lot of projects on fair data, NLP, natural language processing programs, and we develop a lot of software and tools and infrastructure, and that's what I'm going to present to you about today. But first, do you remember this photo some years ago, the early days of the COVID-19 pandemic? We did not know anything about the virus, but still we needed treatment, right? Do you still remember the early days? You don't? It's just lost in your mind. Lost in time. So there was a huge challenge from many different perspectives, but one of the challenges for medical doctors was what kind of treatment did they need for all those patients? And one of the tasks for medical guideline experts is to come up with medical guidelines as quickly as possible. Normally a medical guideline takes about a year, sometimes 2 years, but back in those days we did not have any time. We needed guidelines within a day or two maybe. And this is where actually one of our projects accelerated, because we were actually trying all kinds of machine learning techniques. This was the era before ChatGPT, right? So we were already working on all kinds of language models and machine learning solutions to quickly get an overview of the scientific literature. So the question was, how could we use AI and all kinds of techniques, NLP techniques, machine learning techniques, large language models, small language models, to quickly get an overview of the literature? So normally, if you need an overview of the literature, you search in a database. And then you write a protocol. Boring. And then you search the literature. You find maybe 10,000 records if you search in PubMed, a database of scientific literature. And then someone has to go through all those records to identify the few that are relevant to your use case. So we're also collaborating with the Dutch Child Pediatric Formulary. They try to come up with dosage recommendations for children. You don't want to miss that very one paper that describes side effects for your child, right? So the task is not like a simple Google search to quickly find one paper or website or text. No, we want to find all of them, also the one that describes side effects. So the challenge is how to screen that literature. Typically a task performed by humans. Did any of you publish a systematic review or meta-analysis? Okay, so there are a lot of scientists, information specialists, medical guideline institutes, the European Food and Safety Authority, for example. Behind every food product, there are systematic reviews behind it. Behind every medical guideline, there's a systematic review. An overview of the scientific literature on that particular drug or that particular food ingredient. And it's truly the case that all these humans go through thousands and thousands of papers. And back in the old days, well, they're still doing it like this. They go to the library, they download the PDFs of all those scientific papers. They take the first, they read it. No, not relevant. Second, no, not relevant. And they can read about 50 papers per hour. Can you imagine how long this is taking? So the next time you go to the doctor, and this doctor tells you, oh, you need, I don't know, surgery. And realize that a human has been labeling all the papers about that particular surgery by hand. And this is an enormous task. The problem is that we scientists, we publish way too many papers. So there's this exponential growth of the scientific literature. And now with ChatGPT and all these instruments, we're actually producing even more papers. So getting an overview of the literature becomes harder and harder and harder. So imagine that these are all the scientific papers published on any topic, and you want to create an overview for that particular drug, or that particular food ingredient, or treatment for depression, or whatever. Then you search the literature, and depending on your search criteria, you will identify more or fewer papers. And the trick is to find all of them. That's the use case of systematic reviewing, which is behind all those guidelines. So, about 5 or 6 years ago, I was actually working on one of such a systematic review myself, and I'll give you a little example about the topic. And then I thought, well, can't we use a machine to help me with this boring task? Because typically, and that's what you probably know, boring tasks can be automated. So why the heck would a human screen all those papers? Can't we develop a machine that does this for us? So you feed the machine with the 10,000 records that you identified in the search, and then ask the machine to create an overview of all the relevant ones. Now the problem is that this seems a very easy task, but actually it isn't. So there are a lot of steps in this systematic review pipeline, starting with the formulation of the research questions, searching in the databases, screening through the literature, data expression. There are many, many different phases before you can actually publish a medical guideline, for example. But the one about sifting and selecting studies, that step is taking all the time. Okay, so I thought, well, let's create a tool that can do this automatically. So first we started creating an overview of existing tools, and there are quite some tools that actually do this, but none of them is open source. The only one that we developed, that's AS Review at Utrecht University, is actually open source and consists of open code. And that's why we're here, right? Also, many of the existing software packages, they only have one machine learning model implemented. But also look at the questionnaires here. For some of the tools, we don't even know what language model they used, or what classifier they used, or what machine learning they used. I'm not going into all the details here, but I think this is quite worrisome. So I like open source software. Okay, again, the task. You do a search, you find a lot of records. The task is to go through all of them to find a few that are relevant to your research question. Can we use a machine? Yes, but not a black box. So I prefer an open source, transparent, reproducible pipeline. Right? And especially nowadays with the AI Act in place, they have to. So this morning I was talking to a medical guideline somewhere in Europe, and they're creating a new medical guideline for a certain disease, and then we also discussed, can we use AI? And then they concluded, only if it's open and transparent and if the source code is available, so that you can actually check how the AI actually performs and how the AI is implemented and what it does and what it does not do. So I'm going to give you a little bit of background information about how this systematic review task works, and then we delve into more the code and the parts that are maybe more of interest to you. Okay, so you do a search, you find a lot of records in multiple databases. The first task is to merge all the databases together, deduplicate all the records, so you don't want to screen the same record twice. And then either you start with this random, the traditional phase, and this literally is what most of the screeners still do. They take a random paper from the pile, they read it, they make a decision whether or not it's relevant, they take it a second, the third, the fourth, and they go through this pile of records, days, weeks, months at a time. What we propose is actually to replace this with an active learning pipeline. Is someone familiar with active learning? Because active learning is quite known in the machine learning field, but I'm not sure if... So, okay, now I'm going to explain how this works. So with active learning, we're not going to replace the scientist with a machine. We're using machine learning models to propose the most likely relevant paper to be read by the human. So we have two cycles. So we have a data set, and the data set consists of scientific publications. Consider 5,000 papers to be read. And then while the human is reading, the machine is training a machine learning model, and this machine learning model proposes the most likely relevant record to be read by the human. The human provides a label, then this label is fed back into the machine. The machine uses the label data to predict the relevance of the unseen papers. The human labels a paper, and then you have this interaction between the machine learning model and the human. So after each labeling decision, the machine becomes smarter because the training data grows. So you can start with one labeled record, then you can train a machine learning model only on one labeled record, yes. The relevance scores are very unstable, of course, but at least you can start. But every iteration, the machine becomes smarter and smarter and smarter. So you start with a pool of unlabeled records. You have this annotator. The annotator reads one record. This annotator provides a label, so it's moved to the labeled side. The machine always picks all of the labeled records to train a machine learning model. It produces relevance scores for the unseen records. The human labels the most likely relevant record. It's pushed to the training set. And this iterative cycle is what we call active learning. I didn't invite active learning. This is very popular in many machine learning applications. And often, the machine learning model, the model itself is the output. Because then the model can be used for future data sets. So most machine learning applications are about a perfectly performing model. We don't care about the model. We only care about finding the relevant papers as quickly as possible. Think about this COVID-19 situation. We wanted to know as quickly as possible what treatments were actually effective and what treatments were not. We didn't care about the model at all. We just want to know the relevant papers as quickly as possible in the process. It's just clear because this is a 2-minute introduction to machine learning. Go ahead. Yeah, that is a good question. Why don't you let the machine label all the papers so that you come to the doctor and the machine tells you no? Do we want that? Maybe not, right? So, depends how good it is. Ooh, okay, yeah. But I think that most people don't really like it when the machine tells them not to go for surgery because the machine decided a paper is not relevant. Right, so what we strongly believe is that the human is the oracle, and the human makes the labeling decision. That also means that the human is responsible. So what if the machine makes a mistake? Who is then responsible? Is then the human using the machine responsible? We who created the code, or go. Yeah, that's a good question. So let's say so I will give you an example in a few more slides. Yeah, so if you can wait with this question, because that's a very excellent question. So out of the 5,000 records, maybe only 38, that's the example, only 38 are relevant. But you don't know when you start labeling those records. So that's why you also need a human, an expert, who can decide, okay, now I've seen most of the literature, and then I decide to stop. Yeah? But I'll come back to your question in 2 or 3 slides. You also had a question.
Yeah, you mentioned something about stability.
Yeah.
And also a little bit curious in how big of an influence it has that maybe the researcher mislabels, because that might also happen. What's your idea about that?
Yeah, good question. So you're actually concerned about a human making mistakes. Right, so you're more concerned about the machine making mistakes, and you're more concerned about the human making mistakes. So there are quite some papers published about the human bias, and about 10% of the labels by humans are wrong. Either false inclusions or false exclusions. And that's why at least 2 screeners have to go through this pile of records, hoping that that one of the 2 at least finds this paper. So the machine, the only thing that the machine does is producing relevance scores. And with more training data, that's what we know, right? More training data, better machine learning performance. So the longer this iterative process continues, the more stable the model becomes. But you have to think that that most labeling processes take at least 1,000 decisions before a human stops. So you will produce a lot of labels on the fly, so that the machine learning that the machine learning model becomes quite stable at some point in time.
Is there still a possibility that you miss the most relevant document? Because at 1,000 loop times, you say, okay, we have enough data, but just you're missing
Yeah, so this is again a good question. This is again about stopping this iterative cycle. So what we've seen in a lot of simulation studies, and I will show you a couple of those, what we see is that if you switch to a different model throughout this process, so if you start with a very simple model, so for the people who are familiar with machine learning models, like you start with TF-IDF and logistic regression maybe, and after 1,000 labeling decisions, you switch to, I don't know, SBERT, a more complicated feature extractor, and maybe a neural network model, so that you just reorder the entire pool of records. That helps. What also helps is that in this systematic review process, you never stop with this screening. You always go to experts in the field. You always ask around what are the papers we should not miss, the certain cornerstone papers or the golden papers. But you also do not want to rule out that one paper published outside of your bubble. So we are currently doing a systematic review where we included about 20,000 papers. And we know all of the people that publish on this topic, the Americans, the Dutch, the Germans. And then at some point we found one Korean paper, completely outside the bubble, but very important because it provides some insight in how this topic, post-traumatic stress, is actually discussed in Korea. We would never have found this if we would simply ask our fellow Dutch and American scientists because they're not unaware of that paper. Published in Korean, in a Korean journal, which was not indexed by all the American databases. Right? So there's also bias simply because we live in a Western bubble. So far, so good? Yeah, go ahead.
This unsupervised learning, that is also, that's more of a labeling thing, right? When we do not label the data but provide it to the machine and then the machine decides what label to put on.
Yeah. Yeah, so you refer to unsupervised learning. Well, this is actually just in between unsupervised and supervised learning, right? So we start with unsupervised learning, we provide a minimum training set, so then we switch to supervised learning, and then we get reinforcement learning, right? So the machine is updated every iteration. So every time the training set increases with 1 unit, a new model is being triggered. So this is basically reinforcement learning after every labeling iteration. Yeah? So far, so good? Yeah?
If the model gets better, does the machine take a new look at documents that have already been seen but might be addressed based on the new skills of the machine?
Yeah, so that's a good question. So you ask, if the machine performs better at the later stage in the process, will it then re-evaluate papers at the early stage? No, not by default, but what we always advise to do is to retrain a model on the excluded papers, because all the papers that are included in this phase will be pushed to the data extraction phase, right? And if in the data extraction phase it appears that the paper is not relevant after all, it's just deleted, right? So we care more about the papers that are excluded in this phase because no one will look at those papers again. So we apply what you suggest to the excluded papers, not to the included papers because these will be read by a human in a later stage anyway. Yeah?
So you have very much look for relevant or not relevant as something black or white.
Yeah.
So have you also looked at like maybe giving it like a score?
Yeah, so good question. So yes, it's now a dichotomous decision, relevant or irrelevant. And you're asking about, can you not give a score? So yes, the output of the machine learning model is a relevant score. Or if it's a logistic regression, it's actually a probability, right? Yeah. But if you have a 16-layer neural network model, it's not like a probability, it's like something, right? So that's why we call it a relevance score. So the machine produces relevance scores. We simply rank order the papers on relevance scores and show you the highest one ranked in the list. We ask the humans to make a dichotomous labeling decision because what would happen if we would have one more category like uncertain? Then those records that are most informative to the machine learning model will be labeled as maybe. Because those records are exactly what separates the set of included papers and the set of irrelevant papers, right? So we really force a human who is the oracle to make an informed decision precisely on those records that are just in between relevance or irrelevance, because that information will trigger the best model. Yeah?
Yeah, I was also thinking about this, like the set that you keep out, and then want to re-evaluate, so to maybe only take a cutoff there.
Yeah, but where to put the cutoff? That's the whole thing. Right? Shall we put it at 0.05 or 0.50 or 0.65 or 0.42? Who cares? And then for a logistic regression model, we maybe know what the value means, but again, a neural network, do we know what the values mean? They're not the same as the output of a logistic regression, so a cutoff used for one model cannot be applied to another model. And then again, think about you visiting the doctor and the machine tells you, well, this one paper describing side effects was just below the cutoff value, sorry. Right? So even a paper with a very low probability score can be extremely relevant. Not saying it is, but it can be. So that's why we leave it up to the expert, the human, the oracle, the clinician, to make the final labeling decision.
Maybe like a Korean paper.
For example, this Korean paper. Okay, an example. And I realize on the next slide, you will see some photos. And this is a project in collaboration with all kinds of treatment centers for post-traumatic stress. So we run a lot of studies together with victims aid, slachtofferhulp for the Dutch, victims aid, emergency rooms, the Dutch burn centers. And we're often interested in the question, who will develop post-traumatic stress after a traumatic event? If this triggers something for you, just close your eyes. I will just show you a couple of photos just to realize what we're talking about. Yeah? So here you see burn victims. So we run a lot of projects with small children who get severely burned. School shooting here, 9/11, hurricanes, all kinds of disasters. So the question is, can we predict as quickly as possible who will develop post-traumatic stress? Because if you go to the emergency room after such a traumatic event, we ask you 3 questions and we tell you, oh, you're resilient. Just go home, talk to your friends. That's enough for you. Maybe someone else needs therapy right away. Right? So we use all kinds of machine learning models to predict who can actually, who is developing post-traumatic stress, who needs help and therapy. For one of those projects, we actually needed an overview of the literature. So we found more than 6,000 papers to eventually only include 38 in this overview. So I read more than 6,000 papers. And literally, I started Monday morning, reading paper 1, paper 2. On Tuesday, I found my very first relevant paper. On Friday afternoon at 3 o'clock, it was time for a drink, right? Weeks, non-stop. So after deduplication, after cleaning the data, there were 5,100 papers. Let's assume we start on the left-hand side. There are 38 relevant papers hidden in this data set. How many papers do you need to read as a human using the classical traditional pipeline to find all the 38 relevant ones? This is like an exam, right? All of them, yes, exactly. So by chance, you will find a relevant paper every now and then while reading the 5,000 papers. So now the question is, using machine learning model, using this active learning approach, can we now push all the relevant papers to the front of the reading process? So on the next slide, you see an animation. You see 2 screeners. One screener following this gray line who randomly reads the paper. Every time the line bumps up with 1 unit, this person finds a relevant paper. And you see the lucky one reading in interaction with this machine learning model using active learning. So that's the green line. Guess who's done first? So the screener who finds the 38 relevant papers first is the winner. Here you go. The gray one, first paper, yes, 300 papers read. The second paper, third paper, shoot, the other one is already done. So instead of reading 5,000 papers, I could have read only 300 papers and already find the 38 relevant papers. Whew, that's a huge difference, isn't it? Well, okay, this was my study. You can, maybe the model was optimized for my particular data set. So here's a different data set. So this is from the Center of Mental Urban Health in Amsterdam. It took them 2 years to read 50,000 papers on theories of depressive relapse and recurrence. 2 years, yeah? So I ran this simulation study for them to find out how much time they could have saved. And I was so happy when I presented the results. So I presented them this result like, oh, after only screening 5% of the papers, you would have found almost all of the relevant papers. What is 5% of 2 years, right? And then 2 people in the room started crying. It were the 2 PhD students who read the literature for 2 years. And I realized, oh, shoot. You know? So this is the enormous amount of time you can save using these kind of models. We have developed software to do this, so user-friendly software, which you can easily install, and it looks like this. You can select a machine learning model. I'll come back to that a little bit later. And then the system simply presents a paper to you, and the only thing you have to do is click irrelevant or relevant. Last week, we were, I don't know if you've seen the local news, but we were in the Dom Tower. So I hired the Dom Tower, and there were 40 participants of an EU project. They all came to Utrecht, and we screened 12,000 papers in just 2 days. 12,000 papers in 2 days. Think about these poor PhD students who were reading 50,000 papers in 2 years, right? Don't tell them. There's also a hidden memory game. Okay, anyway, now the fun begins, right? So I like open source code. So this is a completely, fully open source project, and not only the source code is available, but also what we care about is that this interaction is completely reproducible. So you can go back to any stage of this iterative cycle and find out what the human labels are, what the machine learning output is, etc. That means that you can also interact with the software at many different layers. So written in Python, you can interact with it on the Python level. We have a command line interface, REST API, the ASReview Lab tool, which you can install locally on your laptop. You can also install it in the cloud, put it on a server. If you want to give it a try, if you go to asreview.app, you can actually play around with it. Everything is on GitHub. So if you have questions about it, I can show things on GitHub. And we have extensive documentation, so interested. Yeah, the Netherlands is only on place 10 of the most installations. So we're very popular outside the Netherlands, but also inside the Netherlands. So all the medical guideline institutes are using it, the RIVM, the Planning Bureau of the Living Environment. So all of those institutes that need to screen the literature are actually using it. The great thing is that ASReview Lab is only the screening interface, but that's just one of the many software tools that we actually offer and produce. Because what we care about is to find out what machine learning model works best for what type of data. So if you have a labeled data set, and there are many labeled data sets, right? So every medical guideline consists of a labeled systematic review data set. So we know the thousands of papers they have screened to create a medical guideline or a food safety guideline, or any meta-analysis or systematic review contains a labeled data set. So what we can actually do, we can actually mimic the labeling process. And then that's what we do in our AI lab. We try to find out what are the important ingredients to improve the performance even more. So is that, for example, pre-processing the data in a better way? Getting rid of noisy labels or duplicate labels? What kind of data do we feed into the machine? Are it titles only, or abstract, or full text? People have also been using the New York Times database, newspaper articles, tweet messages. Basically, you can put in any type of textual data. But then the quality of the data matters. For example, we once processed narratives of teens describing the major turning points in their lives. But what we didn't realize is that teens also use slang, and not every teenager is very good at writing very nice sentences like we scientists do in our abstracts. So that requires a completely different model, right? So this is all about the pre-processing parts. What kind of model can you actually use? A multi-language model, a very simple model, a very complicated model, maybe even a large language model for doing this. And then you have also all these stopping rules, when to stop screening. Well, for all of this, we have all kinds of software tools, we run projects, we have many different PhDs working on this. So for example, data sets. We have a lot of...
Oh, sorry, can I ask a question?
Yeah, of course.
Quick about the last slide. So you said you use the data set of the labeled systemic reviews in the past. But
Yeah.
do those data sets also contain the unlabeled?
Yes.
Okay, because otherwise it would be difficult, I guess.
No, you need a fully labeled data set. So if you identify 10,000 records in your search, we need 10,000 rows and a column with the labeling decisions, zeros and ones for every single record. So, for example, a scientist or a medical guideline expert publish a systematic review or meta-analysis, and they publish their data on what we typically do on the Open Science Framework. So you simply put this Excel file or this tabular format file, whatever format they have, they push it to the Open Science Framework. And then what we do, we harvest that data, and we push it actually to what we call the synergy data set. So the synergy data set is one of the benchmark data sets that we're using, and it consists of, where are we at this moment? 82 million trainable data points, and we keep on adding more data sets. And this data set is now downloaded more than 1 million times for testing all kinds of pipelines, finding out what kind of machine learning models to use, etc. Then the question is, what model to use, right? We have a lot of models built already into the software, so you can simply select one of the models. But basically, are you familiar with Hugging Face? You can basically take any model from Hugging Face, plug it into the machine, and then test whether that particular model outperforms any of the other models. And then you can get actually these kind of overviews where every recall line, so far we only saw one recall line, but you can actually compare the performance of different models. So can we squeeze out a little bit more performance? And then you would say, does it really matter? Well, that's the difference between reading maybe 3,000 papers versus 500 papers. You can read about 50 papers per hour, so you can calculate how much time you can still save by switching from, well, what is the worst performing model? The gray one, random forest and doc2vec. And the first one is naive Bayes and TF-IDF. Right? So it matters what model you pick. Also, for example, here we have a different data set that contains 4 papers, or at least 4 papers, written in different languages. And if you simply use TF-IDF and naive Bayes, those records will not be found. So can't we not use better feature extractors? So there's this whole list of feature extractors that translates text into information a machine can use. And does one of those models then work better? Yes, the newest model by Google actually finds those papers just as quick as the English papers. And this was before all the large language models came in, right? So this was even before the era of ChatGPT. So what you then can do is not run just one simulation model, but here is a result of 20,000 combinations of different machine learning models and different data sets. So that you can actually create these kind of overviews, where on the x-axis you see different systematic review data sets. So for example, the one we just discussed is this one from the Schoot 2018. And then the performance is on the x-axis, the work saved over sampling. And as you can see, so this is a summary of thousands and thousands of simulation studies combining different models per data set. And as you can see, for some of the data sets, you get almost perfect performance. Hull is a software engineering paper. And it doesn't really matter what model you pick, you always find all the relevant papers, almost immediately. But you can also see that for some papers, there's a lot of variance. There it matters what paper, what model you pick. And for one data set over the left, you don't save so much time.
Question?
Yeah.
You say several times all relevant papers. If you have a data set, you do not know how many relevant papers there are. If you use a model, it decides, oh, this is relevant or is a score or not. So with using the model and not see every piece, you always have a chance to not find all.
Yeah.
I don't think it's that's a bet that you don't have all papers, because if you find 98% of but why we use
Because for these, so the question is, why do I use the term all? The reason is, for these data sets, we know. But for an unlabeled data set, if you start from scratch, you don't know how many labels there are. And that's basically the problem of any machine learning application applied to this use case. You don't know how many papers there are. You even don't know if all the papers are part of your data set. Think about this Korean paper. If I would have simply searched in the classical American databases, I would have never found this Korean paper, which was published in a journal, not even indexed in the database, the Western databases, right? So I would miss this paper by default. And then you also have within your data set, simply because of screening fatigue, as a human, you simply miss the paper because it's Friday, 4 o'clock, time for drinks, right? So that's a second reason for bias. And then the third reason is, and that's only where the machine comes in, the machine learning model cannot present it to you because it's not recognized. Think of these poor non-English abstracts. The machine does not recognize that these abstracts are relevant to you simply because it cannot deal with non-English text. If you then use a better model, then at least this bias is solved. So that's what we try to do. We try to find out what type of data needs what type of model. And then if you have a new data set, then we can say, this model works best for you. Right? Yes, you can ask as many questions as you want.
So the x-axis is like on the previous slide is the data set.
Yeah.
The y-axis is like the difference in models.
Yeah, so the y-axis here is work saved over sampling.
But by several different models, right?
Yeah.
Yeah. But I can imagine, like, my assumption would be that these models are also non-deterministic. So do you also have so it's actually a 3D kind of graph, right?
Yeah.
So how does that work in your research?
I'm not very good at 3D graphs, that's
Me
one.
neither, so I'm glad you use this one. But I can imagine that there's also it's not non-deterministic, so you don't know in advance how the performance is going to be. Because there are also studies done.
Yeah, so what we try to do is we try to resample as many times as possible. So we're redoing a lot of these simulation studies with slightly different starting points, different seeds, different training data starting points, just to get an estimate of model uncertainty. And as you can see, for example, this Hall paper doesn't matter at all. And then if you look at one of the papers here with this big variance, this, what was it, this Chow paper, there it matters. And we not only differ the type of model, but only the starting paper, the seeds. So that's how you end up with what is it, 23,000 simulation studies. To get a feeling of model uncertainty.
Because you were talking about performance earlier on. Like, I can imagine that performance is a trade-off for maybe the discrepancy in actual result, right?
Yeah.
As well.
Yeah. And then briefly, just to show you how this works, is running simulation studies can easily be done in the front end. So there's this option, do a simulation study, you upload your data, and then it works. We have this huge command line interface where you can actually provide seeds, select different models. We also have this template generator that can actually generate hundreds and thousands of lines of code, varying, as you can see here, different seed values, different starting papers, different models, to run this complicated simulation model. I'm not going to explain that. And running this can be done on your laptop, but at some point your laptop cannot deal with it, and then we end up with Kubernetes clusters to do this in parallel.
You just showed like a lot of big systematically building. Does this also work for like small, like literature studies maybe?
Yeah. We've run some simulation studies with only 400 cases, up to 1 million cases. But if you only have 400 records, I've not seen a bare minimum, but so if you think about time to save, how much time can you save if you have only 400 papers to screen versus 100,000 papers to screen? There's more time to be saved, right? So I'm not going into all this to this detail, but for the people who are interested in Kubernetes clusters, this can just be parallelized. I'm not going to explain that here. So, questions? Time to relax.
Yeah, I was wondering
Yeah. We're actually also publishing a paper where we claim it's now unethical not to use these kind of techniques, right? So now that we know that all these tools and these machine learning models are actually this good, why would you not use it?
Yeah, because at first I was also thinking like, okay, this removes the learning that the students have in like labeling these relevant or not relevant. That's actually like the core element of this.
Yeah, but think, yes and no, because what we see is that the most likely relevant papers are pushed up front, and all the crap, all the papers that are far away from your research question, you will never see. So what will happen is that you read all the papers that should exist in your introduction section, but also all the papers that are very close, because that's the order in which all the papers are presented to you. The question should be, right? Dear ChatGPT, can you do this for me? Because that's where the students are right now. Like, why should I read at all? You have a question?
Have found biases already in your models when you were training them, and you found like, oh, maybe it's rejecting now models,
Yeah, so what can happen, so remember, the model does not reject the paper, but what can happen is that the model does not recognize that a particular paper written in a different style, for example, is also relevant to you. And that's where you need to train a different machine learning model that also takes context into account. So that it are not, if you need to leave for just run away, just say, oh, this is boring. And we're also almost done, I think, right? Yeah, so 2 more minutes and then... So yes, this happens, and then what we advise to people, train a different machine learning model that takes context into account, or a completely different model to reorder the papers you have not seen in a different way, so that those papers that might be pushed low by the first model are now presented to you first. Yeah. Last question of the presentation. Yeah, good question. We don't reuse our models.
Okay.
We always train a model from scratch. Because the reason is that it doesn't take so much time. Many of the models are done in seconds.
And you need labeled data to train them, right?
But you need to start with one labeled data point, or basically 2. One relevant paper and one irrelevant paper, because then you can train a logistic regression model. So start with a very lightweight model, and while you're reading and labeling, at some point you have 1,000 labels, then you can trigger this very complicated neural network model. Yeah, no, I'm sorry, this was the last question. I will stay here. If you have more questions.
There was a question unanswered, because one I think you asked, can ChatGPT do not...
Are you doing this?
Yes, so here's the prompt. Yeah, but the problem is you spend a lot of fresh drinking water, and what if ChatGPT tells you that the paper is not relevant, and there we are, you visiting the doctor, and then the machine tells you, no, you don't need surgery, because ChatGPT just told me so. Right?
The same accounts to human effort.
Yeah, exactly, yeah.
So
Yeah.
isn't it unethical to not explore?
And that's exactly what we're doing in our AI lab. Okay, people. Yeah, so if you're interested, visit our AI lab. Every Thursday we work together with developers, with scientists. Just visit us, and then you can actually see how we're doing. Okay, cool. Thanks, people.